All right, so first of all, thank you very much for inviting me and letting me be the first speaker of this session. And given this position, I decided to talk a little bit more general on clocks rather than to just specifically focus on one of the clocks we have made. If you want to see more about that particular clock, we have a poster on this as well where we have lots more data and you can look at the details of that. But let me start with asking, why do we want to make clocks? Why another clock? I know some people have this perception that there are already way too many clocks. You can pick your biological age by just picking the right clock and then pick one you like and decide that you believe in that one. So why make biological clocks in general? And one of the answers is, and I'm going to harp back to some old data of mine from years ago, or well, my lab's still doing this, but I did a lot of my work in my own, when I started my group, working on invertebrate models of aging. And I'm going to show you one little slide on C. elegans. So these worms live about 30-ish days maximally. And so if you look at a cohort of these to the microscope at about 28 days of age, what you're going to see is this. So this is a little video of these worms at 28 days, and most of them are dead, because at that point about 80% of them are dead. And then there are some stragglers who still do their best to hang on, but they are sick, they cannot move properly, they're constipated, and if they could express an opinion, they would certainly say that they don't enjoy their life very much at this point. But they have 302 neurons, so not many opinions being made. But if you look at an intervention, and this is from my lab where we did work on drug synergies, you look at the same animals, so in fact siblings of these, who are treated as adults with a drug combination. And what you're going to get is, at the same age, they look like this. And this is just to sort of make a visual point that we're not talking about living in decrepitude for longer. When we talk about aging intervention, it's really about being younger for longer, or younger again, depending which school of thought you prescribe to. And so these guys are clearly just biologically much younger in every possible way than the untreated animals. And so sure, people will say, okay, fine, this is worms. Worms are simple model organisms, they're invertebrates, that doesn't really apply to me. But if you look at these two individuals here, Tom Cruise and Val Kilmer, in 1986, they were very similar. They were young actors, very successful at the beginning of their careers in many ways. And they're, biologically, one would say, and chronologically, they were very similar in age. However, over the next 40 years, they had quite different trajectories. And the reasons for this are many and complicated. There's lifestyle, there's just luck, there's environment, there's genes. There's all sorts of factors, but it's no question that they aged quite differently. And also, it makes me feel much older to realize that was almost 40 years ago, this movie. But anyway, so over the 40 years, they had a very different experience. And so they diverged in their trajectory quite a lot. And it's therefore fair to say that we know that biological age is very different from chronological age in all animals, including humans. So it's important to know the biological age of an individual and to see which factors determine where on this trajectory you're going to be. And that's why I think biological clocks will be essential to develop aging interventions. So then how do we go about making those? Well, it's very important to think about what's the biological age you're trying to actually measure. So which biological age, which aging are we going to target? And I think one of the things that's very important, or what I think is very important for a convergence of these clock methods in the future, will be to focus not so much on how somebody looks in a given feature space, but essentially to look at mortality. And of course, this is where I'm going to talk about Benjamin Gompertz, a Victorian actuary, who essentially discovered that the risk of dying in humans doubles every 8 years. So this is the mortality risk, and this is the age, and so it's 2 to the power of age divided by 8 years in humans. So this is what the curve looks like. Last year at the same conference, Andrew Steele told us all not to use log plots to show this graph, so I went back and redesigned the whole slide with a non-logarithmic scale so that you can see the exponential increase in mortality directly. So on the x-axis is age, and on the y-axis is mortality risk. And so what you can see at 10 years of age, you have maybe a risk of dying of 1 in 10,000 in a given year. 8 years later, this is double, and so by the time you're 40, the risk has increased to about 1 in 600. By the time you're 60, the risk is about 1% a year, and by the time you're 80, it's about 1 in 20. So this is quite a steep increase in risk, and you can see that you're going to hit a wall there very quickly. But what's important that relatively small differences in doubling time if individuals, because of all of these factors, lifestyle, drugs, genes, environment, might have slightly different mortality rate doubling times can have quite large effects on this. So if you did the same for a doubling time of 10 years, which is really only a 20% difference in aging rate, then essentially somebody at the age of 80 has the same mortality risk as somebody on the normal curve at 60. So you can get a statement that by the age of 80, this person has a biological age of 60. And this is exactly the mortality definition, or the age definition that we use for our clock. So it's the risk, it's the age at which your risk of dying would be typical for the reference cohort, not where you look like the reference cohort. And so this is a mortality as an outcome. Now, at this point, people will often say, well, yes, but we're all about health span, right? Why do you keep talking about mortality? Why are we making mortality clocks? Why not do health span clocks? But really, humans don't die of some magic old age thing that happens to them where they're perfectly fine and then their lifespan runs out and they're dying. What they're dying of is a reduction in the resilience. So in other words, the same challenges that would not kill a younger individual might, kill somebody who is old, who has a lower resilience, and COVID was a perfect example of this, which killed to a large extent older individuals. And then the other thing, of course, is that people will die of age-dependent diseases, which are morbidity. So this mortality clock will, of course, also track mortality. It will track mortality, it will track morbidity and the reduction in resilience, and those are very tightly linked. So therefore, I think training on mortality, which is the best data that we have usually because it's much more difficult to get longitudinal, for instance, activity of daily living data on large data sets, is a good way to go. Okay, so that's a slide about Singapore. So we have this program, this Healthy Longevity Translational Research Program, and the agenda is to essentially build on these omics markers and including biological aging clocks, use those to identify interventions, then iterate through these interventions in shorter trials using the clocks to inform the development of the interventions and the testing, and then go back and cycle until you have a lifestyle intervention, drug intervention, dietary intervention, or any other modality that leads to essentially a reduction of biological aging rate and increase in healthy lifespan. So that's the purpose of this. But I have this whole pyramid here, and you can ask, well, yeah, okay, but so, you're making epigenetic clocks, are you making lipid clocks like Max talked about? Are we going to proteomics clock, what should I be using? And my answer to this would be whatever is most convenient, what you have data for, and what might be most informative, because really you should be able to get ultimately the same answer from any one of those feature spaces. And the reason for this is that, of course, all of these are slices to the same regulatory machinery that determines your physiology. So DNA methylation changes will affect transcript levels will affect levels of metabolites, lipids, and proteins. Changes in those will affect metabolism. Metabolic changes will be visible in clinical parameters, in things we already measure routinely in the clinic, and ultimately have manifestations in physiological features and performance. So it should really be possible to extract aging signatures out of any of these feature spaces as long as it's high quality and you have enough of it. So in that case, then, what should we do? How do we get these aging signatures out? And at this point, I'm going to ask for your indulgence to channel the inner physicist in me and do the trick physicists always do when we face a complicated system or problem. We will discuss it either in less than 4 dimensions or infinitely many, because that's about the only thing we know how to do anything about. So I'm going to show you a 2-dimensional example of this, which will be illustrative and of course isn't evidence. It's just an illustration of the kinds of things that I think we should be looking for. So physiology in feature space. So you can have a 2-dimensional space that can track any kind of physiological parameter. So it could be something as simple as LDL cholesterol and blood pressure. Or it could be catabolism and systemic inflammation. Or it could be 2 different parameters like gene expression patterns of some sort, PCs of a transcriptome, whatever you want to do. In any case, you're going to have some sort of physiological state that's representative of a healthy young individual, so where you should be. And you're going to have some area around that space, which will be essentially the area where normal physiology takes place, like environmental, day-to-day stochastic variations will move you around in there, but it's all still normal, healthy physiology. And then you're going to have some sort of places in feature space that are, disease or failure attractors. In other words, if you get pushed into this region, this is associated with, ill health or catastrophic failure or some other negative outcome. And it's the job of your gene regulatory network, the one I just showed you all the feature space slices through, to essentially keep you in that place. And so physicists like simple things, so 2 dimensions is great, and then simple spring oscillators are great because that's another thing we know how to do anything about. So essentially you can imagine that the purpose of this whole complicated gene regulatory network is to return you to the physiologically normal state if you're facing perturbations. And of course, you can replace the springs with some sort of returning potential, which is a 3-dimensional potential that essentially tries to return you to a normal physiology, and then there are 2 attractors that are failure. It's just a way of speaking about the same idea. And then you end up with a picture like this, where you're this little red ball there, and you're in a normal physiological state, and when you're subject to little perturbations, you bounce around in this ball, and that's day-to-day variations. Maybe you have a long flight, and then you had too much beer the evening before, and it's things are a little bit out of whack, and then you rest and you return back to normal. And the person here is like Wolverine or somebody like that, where almost any perturbation they will just return back to normal, and that's how young people look like. So if you put a lot of people in there, 25 in this case, they will all do some uninteresting thing of bouncing around the normal, healthy physiological attractor, and then not do anything surprising. But coming back to another old story of mine, measuring oxidative damage, one of the miracles of that was, or one of the, no, not miracles, mysteries of that, was that there's a small linear increase in oxidative damage that was never strongly causally linked to survival. And so how do you motivate exponential increase in mortality from like a small linear doubling of oxidative DNA damage to mitochondria in this case? And the answer is, of course, that what any damage or entropic input into the system that is not fully removed will do is it will make the system just work slightly less well. That's kind of a trivial prediction that if you break something, it will work slightly less well than it did before. And so what that means in this picture is that your gene regulatory network fades away with damage and in your entropy that remains partially unrepaired, and eventually you get a much flatter potential with less of a returning force. And that's actually a neat way of thinking about it, because if you now put your 25 individuals in there, they again bounce around, but occasionally one falls out of this, overcomes the barrier and falls out of the plane. And in fact, this is a neat model in several ways. One is that this is a linear decrease in the potential. So the red potential is the lowest, bluest is the highest. There's a barrier, but the barrier decreases linearly with time. So you get this linear decrease. But what this will do is that it produces a reduction in potential height. If you want to be a theoretical physicist, you talk about the eigenvalues, changing sign. In geriatrics, you'd say the intrinsic capacity is reduced. In gerontology, you might say resilience is reduced or hemodynamic space is shrinking. But it's a linear change, right? So if you measure this in some way directly, you will get a linear reduction in the height of these potentials. But what this will lead at, if you either calculate it, it's a well-known problem in physics, or you run a little simulation, what you get is you get an exponential increase in the failure probability. So in other words, the linear change in the height of the returning potential very directly gives you an exponential increase in the mortality, which is a neat feature because that's what you expect. The other thing this will do is if you plot different age populations in there, is that you get a movement in feature space. So because the potential gets flatter, the population moves a little bit closer to the failure attractor in this case. And so you get 2 effects. You get a change in the median position of the population or in the median position of an individual's trajectory. So that's the blue to green to orange to red change in location. But you're also going to get an increase in variance. So older individuals are less alike than the younger individuals, and they're somewhere different in feature space. So at this point, you have something that you might be able to explore to build clocks, because you can watch, you can look for those sort of patterns. And one of the simplest ways of reducing dimensionality and finding those sort of patterns is to use principal components. And you've all seen them when you looked at gene expression patterns or like some other data where you show like a 2D PCA. But fundamentally, what this technique does is it identifies features that are covariant or correlated, and then it rotates the coordinate system along the axis of maximum covariance. So it's literally just a linear transformation. It rotates your coordinates. And so now you have a new coordinate system where what's now the x-axis carries most of the covariance. That's called PC1. And really, that's a matrix factorization. So your data matrix can be factored into dominant PCs, and that's a dimensionality reduction. A much smaller number of coordinates gives you almost all your data. And so if you do this with this little picture I just showed you where you have the population in a different place in the feature plane, you can essentially see that in 3D, this points straight at your failure attractor. Of course it does, because that's where your population is moving. So the intuition, and that's all this is that if you look at a high-dimensional data set of any type, where you have individuals of different ages that differ in their chance of different diseases and death, then the dominant PCs will essentially point along axis of failure, and you can use those to make clocks that have much lower dimension than your original feature space, which is important because many of the feature spaces are really big. And if you talk to people who do machine learning, there's usually a feeling that, or the techniques require that you have essentially more examples than you have features, or on the same order. And you have easily tens to hundreds of thousands of features in some data sets, but you certainly don't have easily tens or hundreds of thousands of individuals, especially not individuals with mortality data. It's very difficult to get longitudinal data on 100,000 people with time. So this is a neat trick to do reduction of dimensionality in a way that you might expect specifically extracts aging features. And so you have to quote Peter Fidishev, who's a friend, and he basically at some point, like a few years ago, sat in my office, and he so very nonchalantly said, of course, the first principal component of any high-dimensional data set derived from an aging cohort will always be aging. And it took me a little while to believe that. That's why I talk about it. But it was sort of one of those things that set me off thinking a little bit more systematically about how to maybe extract aging features. And so here's an example that this doesn't just work in two-dimensional toy models. This is another invertebrate model in our lab. These are flies. And so here's a PCA of transcription. So this is thousands of genes. And in fact, the first PC is not aging. It's sex, because the biggest source of covariance in the data set is that they're male and female flies. But beyond that, what you're getting is day 5, day 20, day 30, day 40, day 50 flies have a very clear aging axis. That is also the same in male and female flies. So you can use this to make essentially a one-dimensional clock. You can use the y-axis here directly to more or less infer the age of flies. So it's a massive reduction from thousands of features to one, and then of course you can continue on building more complex clocks on more features. So that was the intuition that led us to say, okay, fine, let's try this in humans. So we've done it in toy models. We've done it with the worms and lipidomics. We've done it with the flies and transcriptomics. We've done it with toy models and simulations. So we thought, okay, let's just do something really straightforward. Let's pick a feature space that is directly actionable. So something where you use biomarkers, everyday biomarkers, cholesterol, blood pressure, smoking status, height, weight, all of this sort of stuff. And we went to the enhanced data set and pulled those out. So it's demographic data, questionnaire data, such as how you're feeling, how did you feel last year, medical examination data, and clinical laboratory data. So you get things like age, sex, smoking, BMI, blood pressure, and so on and so forth, LDL. And so you get 163 parameters. Now, this data set has thousands of subjects, but if you directly run a regression model against 163 parameters, you get a lot of noise from the fitting. You want actually, ideally have more data than this, because you can do it. But so what we did instead is we just did the principal component analysis. And interestingly, you do get some PCs that behave exactly the way I just showed you with my little toy model, right? So there's a clear age correlation of these PCs, and then there's also an increase in variance. That's not all PCs, but some of them look like that. In this case, that's actually loaded for markers of bone density and body composition. So people are more different when they're older, and there is a systematic change as people get older in those parameters. So it's not surprising biology, but it's very readily learned by essentially a model that I feel embarrassed to call, AI. It's really linear algebra and some stats, but it is machine learning technically. And this is actually now in press at Nature Aging. If you want to read the stuff next month, it should come out. So anyway, so we reduced these 163 parameters to 18. So now we have a regression problem with 3,000 subjects and 18 variables. That's pretty manageable. And then we matched it, or we trained it to predict future mortality in the simplest way possible, namely we applied the Cox proportional hazard model for the next 20 years of survival. So this is like straightforward. You essentially have an age delta associated with these PCs, and it's linear. It's just because that's the easiest way to try whether this is predictive. And what you get is something that, unsurprisingly, because by construction it looks like a clock. On the x-axis you have chronological age, on the y-axis you have biological age. And you have these people up here who are much higher in their biological age, as assigned by our clock, mortality age, which is matching. So these are people whose Gompertz probability of dying is much larger than the chronological age would predict. And here you have people who are much lower. And so the question is this actually predictive? Does it learn anything of use? Does it work? And so I show you just one age bin here, centered on 70 years. So this is 65 to 75-year-old individuals. And you take the top 25th percentile and the bottom. And if you look at the people the clock assigns at the largest biological age to, in other words, it says your risk of dying is much higher than your chronological age suggests, then indeed about 20% survive 20 years in this group. So they're very unlikely to live to 90. By contrast, if you take the people that the clock identifies as having the lowest biological age, over 75% of them will live into their 90s. So this is quite predictive of future survival. And it should be, because that's what the model is trained to do. And then you can investigate, because the nice thing about PCA versus like nonlinear dimensionality reduction techniques is that they're very readily interpretable. You can make sense of them. So what we did here is we clustered the feature space. Basically, this is now a two-dimensional representation of the 18-dimensional space. And then we identified demographic features of the people in this plane. And so what you get here is the green cluster are the healthy aging individuals. So the best chances of living a long life, the people in the green cluster, and you can see the survival curve of the healthy aging cluster, the reference cluster above. And then you see the red people who are not really a cluster, they're just all over the place. And this is, that led us to a Tolstoy quote where that happy families are happy all in the same way, whereas unhappy families are unhappy all in their own ways. Sick people are different from each other. They're sick in their own ways, whereas healthy people are all healthy in the same way, at least in this PC representation, which is what you expect. And then the interesting thing is that there is a clear metabolic cardiovascular axis. So if we switch on more clusters, we say make 6 clusters and 7 clusters, it essentially makes more and more slices of this purple and orange cluster. What it means is people have different degrees of metabolic disease, but that's obviously a major feature that the system learns. And so people are mildly metabolic affected at purple, and then they get worse in the orange cluster towards the failure at red. But then interestingly, there's this other cluster, yellow, which we call multimorbid and frail, and these people are not heavy, they're not overweight, and they're not suffering from metabolic disease, but they're equally short-lived. So the orange and the yellow clusters have the same survival, even though they're basically opposite direction in body composition. So then we asked, so what do they have in common? So if they're different, one of them is overweight and the other ones are not, but they have the same survival, what do they have in common? And it's in fact one specific PC. So the question is, what moves you from green to orange or green to yellow? And by the way, the purple balls are the centenarians in the data set, of which there are only a few. Okay, so what makes you go from green to orange and also from green to yellow? What is the same thing? And the answer is it's a specific PC, it's PC4, that's highly significantly different between those two groups. And because PCA is a linear technique, you can then look at the features. You can say, okay, what makes this direction? What are the biological features that drive this? And interestingly, if you then look at the correlation graph of those, you look how they're correlated in the whole data set, and you pull out the top and bottom percentile of this. What you've learned is that essentially they are enriched, or PC4 is enriched for markers of inflammation, fibrinogen, CRP, globulin, and then also has markers of organ failure and metabolic dysfunction, glucose control issues. But interestingly, essentially it's an inflammatory axis. And it's up in both the overweight and multimorbid clusters, they have in common that they have a high systemic inflammation, which again might be something you might have expected, but this linear classifier learned this pretty quickly and easily. Okay, so this brings me to sort of what can we do with this? So we played around, and if you look at the poster, you can see we have data on some ACE inhibitors. We asked which drugs might be affecting this PC. What can we actually see what the effect of polypill drugs, specifically drugs that affect known risk markers of age-dependent diseases, blood pressure lowering medication, statins, and so on and so forth are. And so here's a summary of a lot of stuff we've done, and it's still ongoing. So first we asked, okay, so if we assign a score of optimality, we say which fraction of the population has no abnormal parameters, which fraction are perfect in blood pressure, perfect in cholesterol, perfect in all of the markers. Then you can see that when you're 20, that's 80-something%, and when you're 80, that's only about 60%. This is without drug intervention. So these are people who take no, because NHANES has extensive records on drugs. These are people who are naturally well. On the other side of the equation, if you look at people who clearly by current standards should have interventions but don't have them, in other words, they're missed, that actually raises to over 20% in NHANES. So over 20% of people have something where every GP would say you should be doing something about that, but it's not happening. So if you then ask, does it matter? And you look at those people around 70 again, what you can see is that there's quite a lot of difference in the survival over 10-year follow-up. So the optimal people survive the best, the borderline people next, and the ones that clearly require treatment, that's the treatment guidelines, clearly survive less well. So it's a problem if you're not of optimal health. But these are all people who take no medication. So let's look at that. Let's ask the question, so this is PC4 for this. As you would expect, the borderline people have much higher PC4, higher inflammatory status than the individuals that are optimal. So that's what you expect, more inflammation, less survival. But the question is, what happens if we now add a group which is optimal, but only because they're taking their pills? We take people who are optimal in this parameter space, but they are taking the statin or they're taking the blood pressure lowering medication, the ACE inhibitors. They only manage to be good because they're taking their drugs. And if you look at those in the PC4, what you're getting is there's a wide spread, but if anything, they're even lower than the naturally healthy individuals. So they're better in this marker, or the same, it's not statistically significant, but the tendency is to be lower, and they're certainly the same as individuals who are naturally healthy. Interestingly, if you then look at survival and you split your optimal line here into the no drugs individuals and the polypill individuals, it's actually the polypill individuals that survive better in this bin. So in other words, it seems to be a benefit to be well controlled through medication versus just being, well controlled by, whatever natural process, either healthy habits or good genes. Now, we're still looking at this. This might be a bias that individuals that are on medication and optimal are just taking very good care of themselves and have more access to healthcare. Or there might be something more going on that, there's off-target benefits of these drugs. So for instance, it might be that inflammation is generally lowered by some of those interventions, and we're still looking at them one by one. But a take-home message for one thing we have already learned from our clock, and that we believe is true, is that early and proactive interventions are really important, and that being optimal is really important. And I think that's a huge problem, because if you go to your GP and you say, at my age, oh, I'm borderline for this or that, you will almost inevitably be told, well, try to do a little better, go get some exercise, see you in 6 months or see you in a year. And I think we might be at the point where we can say that might not be the best advice. So I'm personally, and I'm not giving medical advice because I'm not, a medic, but I certainly, for myself and my family, take away from this that it is maybe more important to be in the optimal parameter space than to be free of medication. And I've made choices based on that. Okay, so conclusions, very briefly. I think mortality clocks are good because there's an absolute way of comparing them. If you have a cohort, you have 2 mortality clocks. The one that predicts mortality, survival, death or not, better is the better clock. There's no ambiguity. This clock is still linear. It can't learn U-shaped response curves, so this is clearly a limitation, and we need to do better and use nonlinear techniques, but they're harder to interpret. We're doing that. Because it's a linear clock, it still mixes intrinsically disease and age. It shows the distance from disease attractors, which are strongly age correlated. There's no way of easily deconvoluting this using this technique. but again, there are other ways of doing it. Maybe it's unsurprising that few people are optimal when they're old. Nobody is an exaggeration, but fewer people. Early and proactive is important, and that leaves me to thank people who helped me and supported me in this. Brian, who was center, I have the privilege to work in. Dr. Fong, who is a spectacular geriatrician and who's been working with me on the clock and is also here and has the poster. Peter, who's been fun to discuss these ideas with, and Kirill, who is an AI employee of Gero, who's currently an intern at my lab. So thank you very much, and I'm getting a flashing 0, so I think I'm done.
So I think we'll forgive you and take a couple of questions, even though you're officially out of time. Any questions for Jan?
Yeah, hello. Here.
Yes.
Where are we?
Here.
Yes, thank you.
Okay.
So I noticed that there is quite a broad confidence interval around the mean for the polypill individuals as compared to the optimal individuals. Yeah. And I wonder to what extent the actual medications that those individuals were taking has been studied. For instance, there have been studies on metformin that diabetics who took metformin tended to live longer than non-diabetics who didn't take metformin. But metformin could be one particular medication that has that effect, and it's possible that there are other medications that have the opposite directional effect. So I'm wondering, have you or has someone else investigated the composition of the medication regimens of these polypill individuals?
Yeah, so the original example that's in the paper is ACE inhibitors. So we found that first. It's a bit of a easy example because there's a very clear, strong marker for it that's highly detrimental, and of course you're normalizing, but you're also normalizing the rest of PC4s. That was the original one. There's the metformin example that you just talked about. So we have individual data on the individual drugs, but we haven't dissected this fully. One reason is that, of course, every time you dissect it further, your N numbers get smaller. And so we are merging a much larger data set to be confident with those numbers, yeah.
Yeah, hi. Also related to that, could it be that just the number of pills is important? That there may be a U-curve, too many and too few pills are a factor. Could you find out?
Yeah, so we have that data too, of course. We have tabulated it. There's one polypill drug, 2, 3, 4, and so on and so forth. Yeah. So there's certainly an effect where the benefit goes away when you go to very high numbers. Again, it's difficult to dissect it to 1, 2, 3, 4, 5, because essentially most of them are on 1. And then you get 2, and then if you take 3, 4, 5 and you bin them, that eventually becomes detrimental simply because it indicates that there are several things wrong with that person. But this is still, it's not in the paper. This is still very early data. I just thought it was really interesting. Yeah.
Okay, thanks.
Hey, Jan, great talk. So I was thinking about this, the statement about PC1 always being
Yes.
aging. I'm wondering if this has also something to do about the data. Of course, if you have very young animals, the changes that you see are exponential. So if you've tried to sort of bin the data to become older and older and older, does the PC1 represent aging more and more and more, or something like that?
So I actually think the changes are not exponential. That's one of the interesting things about it. What we see is, so when I was still doing free radicals many years ago, there was this vicious cycle theory, right? You get more damage, and then more damage causes more ROS, and then ROS causes more damage, and there's exponential increase in damage, and that explains exponential mortality. And almost 10 years of my life was spent trying to prove that and measure this in different ways, and it never happened. And it's the same here. There's no feature in this that increases exponentially, in part because most exponential change is probably incompatible with survival. Maybe CRP or something, some of these markers that show really strong effects when something goes wrong, you could make a case that you could fit something like this. But mainly it's linear. But what you're saying is completely true, of course. So if you look at developing animals, the first PC will definitely be development. If you look at children, it'll be growth and development, not aging, although it's correlated with time. But if you mix men and women, then the first feature is sex. If you have a lot of disease, then the first PC might, if you have like a cohort of healthy and cancer patients, it will probably be cancer status. But if you go over the whole life course from adults to old age, then it will be aging. I haven't bent it in subsets of life. I can try.
Last question?
You've had amazing work together with Fedichev, and we've seen a lot of cool clock similar work with Morgan Levine and other groups. One of the things I'm really curious about is, you say more samples for better clocks, maybe nonlinear clocks as well, and better dependent variables like mortality and sort of coronal age and so on. But have you ever seen compelling, for example, power simulations where you can actually say, this is how many, maybe 100,000, more than biobank sized samples, here's how many we need to achieve below 1 year of error?
I think the keyword there is compelling. So I could easily run some simulations with the sort of models that I have here, but you're making an assumption that this is an harmonic returning potential with stochastic noise of a given size, and then you could like answer this. But people are complicated, right? Like so, even just getting the increase in variance is quite difficult because there's so much other variance in actual human data. So the answer is I don't know. I haven't seen any, but I wouldn't know how to do it without essentially feeling like I might be lying.
Thanks, Jan.
All right, thank you.